This is a short presentation of our ECCV paper, Test Time Training with Masked Image Modeling for Denoising Distribution Shifts. So a distribution shift happens when there is a mismatch between training and test sets, which could cause a large drop in performance as seen in this example. So the idea of test time training is to adapt the weights of a trained model to a new test image that comes from a distribution different than the training one. So our goal is to apply test time training to denoise one single image of unknown distribution. So the concept of test time training is fairly simple. You have this Y-shaped model, and it has two branches, with the model being shared between both main and auxiliary branch. The main head is trained with a supervised loss that includes the ground truth, so the regular loss that you usually train with. And the auxiliary head is trained with a self-supervised loss that does not require the ground truth. And the idea here is that you can tune the model and the auxiliary head at test time with the self-supervised loss without having the ground truth, such that the model gets a little bit tailored to the new distribution. So as a self-supervised loss in this paper, we used a variant of the masked autoencoder's loss, which is just reconstructing masked patches, because it has been shown in this paper to be a very good self-supervised loss for extracting meaningful features from noisy images without any ground truths, which is what we want. So here's our network. Here are our two branches, main and auxiliary. We have the model shared between both, and we have the mask here for the self-supervised loss. Now, during training, the main branch is trained with the ground truth, which is X here, as we can see, and the auxiliary branch is trained without the ground truth, so with the masked autoencoder's loss that we showed before. This time, we can easily tune the auxiliary branch with the same self-supervised loss from training because it does not require the ground truth. Now, what do we do with the main head? We don't have ground truth to adapt it. And the original paper that from test time training that was first proposed for classification just left this untouched because we don't have the ground truth. However, we propose to additionally add this part for the test loss, which uses the output of the auxiliary branch O prime as a label to fine-tune the main branch. And since this O prime is not really a clean image, we have to only do 8 iterations, because if we do it for much longer, then we will overfit. Now, the question is, why do we use O prime and why does it make sense? We can try to get more intuition here. So this is the noisy image, which is the input to the main branch. And this is the masked image, the input to the auxiliary branch. And these are the outputs of the main head, and here the outputs of the auxiliary head after each gradient descent iteration with the loss we have seen in the previous slide. This is what we use as the label, those images here. So the question, of course, these images look bad, so why are we using them as a label? So let's recall deep image prior, which I'm sure most of you are familiar with. Takes as input some random noise and uses as target the noisy image, this one. Now, if we look at those images, we can see that with every step, they gets improved a little bit and gets a PSNR even higher than the noisy image. So if the noisy image can work as a target for deep image prior, then this image can work as a target for us as well. So now, comparing to our method, we use as input the noisy image, which is a closer version to the clean image than just random noise. And we use O prime as the target, which is dynamic, so it doesn't stay the same in every iteration, and is also adapted to the new distribution and even gets better than the noisy image, which is why at the end we see that our method only needs 8 iterations compared to deep image prior. So our method can be seen as a variant of deep image prior, where we utilize better inputs, better outputs, and therefore we are much faster. So to test our method, we train a network on ImageNet images corrupted with fixed Gaussian noise, and we adapt it to work well for real-world camera noise, microscope noise, CT images, MRI images, and different types of artificial noise. So we can see here, this is the result you get if you don't do any adaptation. This is the result if you adapt with the ground truth, like the best case scenario. The difference between those two values is what we call the gap, and our method closes around 43% of the gap. And if we compare our method to zero-shot methods, deep image prior and others, we can see, of course, that it is much faster because we don't train a network from scratch for every image like those networks do, but we start from a trained model and we update on that. Here are some examples of our method. So to conclude, I would like to show this simple spectrum. So at the one end of the spectrum, we have the end-to-end networks that are very fast because you only require one forward pass through them, but they are training set dependent and suffer from distribution shifts. On the other end of the spectrum, we have the zero-shot methods, which do not rely on any training set, and they train a network from scratch for every image, but of course, they're very slow because they train from scratch. And we have our method somewhere in between that gets the best of both worlds. So this is the end of the presentation. You can find the links for our paper and code in the description below. Thank you for listening.